Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is meant as a review of concepts from your prerequisite algebra course. As such, I don't delve into the proofs of theorems, nor do I go into excruciating details with examples. If you get lost with the concepts in this video, and it's been a while since you took algebra, I highly recommend watching my full lecture videos on this topic, which can be found in my playlist on YouTube called Algebra, Lots About Linears. There's a series of videos in there on solving large systems. All right, so this is just a review of solving systems of 3 equations and 3 unknowns for a college algebra class. There are 2 main algebraic methods of solving systems that you should recall: substitution and elimination. The former, which is substitution, is used for smaller systems and triangular forms. And what I mean by triangular forms, well, this right here is a triangular form, which means that it's kind of staggered, where you have something like x, y, z, and then y, z, and then z. Notice it's got this triangular look to it. And that's exactly what this is. This looks like a little triangle right there. So this would be considered triangular form. And so again, substitution is great for that, but elimination is used for larger systems. And in fact, it's the basis for a more elegant method for solving larger systems of equations. Now, if somebody has not told you, then let me be the first to tell you, systems of equations are really where it's at. Most of real-world mathematics is done using systems of equations. And so knowing how to solve a system of equations is kind of important. It's not like the average everyday citizen should know how to solve a 5x5 system of equations. That's not true. However, if you go into science or if you go into engineering, systems are going to really be important because you have multiple variables working in it simultaneously, and you want to know what are the solutions to multivariable problems. So let's go ahead and start by solving this system of equations by substitution. Normally, if you were one of my students, I would not tell you how to solve. I would just say solve, and you could choose whichever method you want. But in this case, I'm kind of forcing our hand, saying let's do this by substitution. The main reason why is because it's triangular in form. Another thing I want to mention here is that I normally do not write the brace to say that this is a system. So if I don't write the brace there, I still mean it's a system of equations. And finally, you are welcome to get rid of fractions. So that's my first step almost always when I'm dealing with a system of equations that involves fractions. I just get rid of the fractions by multiplying each equation by its own LCD. For example, this top equation, which I will call row 1, I'm going to multiply row 1 by 30 because that's the LCD of all the fractions within that equation. So I'll just say 30 times row 1 will become the new row 1. That's the notation that we will use throughout this video series. That's the notation that I commonly use in all my video series for systems of equations. In the second row, you could see that I want to multiply that second row by 5 to get rid of all fractions. So 5 times row 2 will become the new row 2. And luckily, row 3, there's no work we need to do. When you do this work, I'll just go ahead and say this implies, and then our system is now, if you multiply row 1 by 30, you get 120x, which does not look attractive, but it is what it is, minus 3y plus 30z is equal to 10. There we go. We don't have any more fractions. And then in the second row, multiplying everything by 5, we get a y minus 30z is equal to a negative 5. And finally, the third row is just the third row. It's just hanging out, waiting for us to do something fun. So there we go. At this point, we can now do what's called back solving, which is basically substitution. You take the equation that's easiest to solve, which would be the bottom equation here, and you would solve. So I'm going to solve that for z. We find out that z is equal to 1/3. I'll box that up so I don't lose it. And then I take that value of z and I substitute it into the second equation, which is y minus 30 times z, which is 1/3. And that's supposed to be negative 5. And then you just go ahead and do your multiplications. So that's y minus 10 is equal to negative 5. Add 10 to both sides, and you get y is equal to 5. Oops, y is equal to 5. Now from this point, we're going to go ahead and take y and z that we just found and plug it into the top equation. One thing I should mention is the most common mistake I will often see on a system of equations problem is that people do bad arithmetic. Very minor thing, but still be aware your arithmetic has to be pretty solid here. So we have 120x minus 3 times the y that we just found, plus 30 times the z we just found. That should equal 10. Cleaning things up here, that's 120x minus 15 plus 10 is equal to 10. The 10's cancel and you get 120x is equal to 15. Or in other words, x is 15 over 120, which reduces down to 1/8 actually. And so we now have our solution set, and you should write this as an ordered triple. So whenever you get a solution to whether it's a 2x2 system or a 10x10 system, you should write it as an ordered n-tuple. So in this case, since we have a 3x3 system, it'd be an ordered triple. If it was a 10x10 system, you'd have an ordered 10-tuple. All right, so the x value is 1/8. The y value for the solution is 5, and the z value for the solution is 1/3. There you go. Completely done, completely solved via back substitution, or what we would normally just call substitution. Now let's go ahead and review elimination. If you don't know Gaussian elimination, then you don't have really an algorithmic method for solving a system of equations using elimination. And so it can be kind of a crapshoot. You basically want to, when you use elimination, choose a variable. Well, first of all, I should say, you should already know to align your variables into columns like this. So in each equation, you basically move all variable terms to the left-hand side and all constant terms to the right-hand side, or vice versa. It doesn't actually matter, just as long as all variable terms are on one side and all non-variable terms are on the other side, then you've got that going for you. Align the variables up in their appropriate columns, like we do here. And then if you're going to use elimination, choose a variable to kill off. In this case, I'm going to choose to eliminate z, because what you're going to do is you're going to add equations together or combinations of equations together so that the variable z disappears. And I can easily see rows 1 and 2 have opposite signs, or sorry, rows 1 and 3 have opposite signs on z. So all I'd have to do is just add rows 1 and 3 to kill z off. Now, when you do this with the 3x3 system, you're going to kill z off twice. If you had a 10x10 system, you'd kill z off 9 times. So essentially, whatever the size of your system is, you're going to eliminate one less time than there are the number of equations. So 3 equations you eliminate twice. Let me label these rows. I'll just call this row 1, row 2, and row 3. That's just a placeholder for where they're sitting there. First row, second row, third row. And what I'm going to do to eliminate z is I'm going to add row 1 to row 3. When you do that, you can just view them right here, row 1 plus row 3. You will get the following. So adding those two rows, you get 5x, because 2x plus 3x is 5x. You have 4y plus a negative y. So in other words, you have a 3y. And you'll have a negative z plus a positive z, so they cancel beautifully. And then finally equals 2 plus 1 or 3. So that should remind you of that. And then you choose a different combination of rows to go ahead and kill off z again. And this time I will choose rows 2 and 3. I will add row 2 to 3 times row 3. You can always add multiples of rows to each other. So let's go ahead and take row 2 and add to that 3 times row 3. Again, you do that so that the coefficients of z are opposite, and so that when you add them up, they cancel each other out. Let's go ahead and see how that mathematics works. I'll take row 2 and add 3 of row 3. So x plus 9x is a 10x. 2y plus, that's my dog barking in the background. Sorry about that. So we had 2y, and we're adding to that a negative 3y, right? We're multiplying that second row, or that third row by 3. So 2y plus a negative 3y is a negative y. Then we have negative 3z, but we're adding 3z, so they cancel. And finally, negative 4, adding positive 3, and we get a negative 1. Now, it is somewhat heuristic what we're doing here, which means basically that deciding what variables to kill off, what variables to keep, is more of an experience thing. You just really try to look for variables that'll easily kill each other off. So in this case, I chose z. If I had gone, I could have easily gone for actually the y's as well. The one that I probably would not have gone for is the x, mainly because they're just not of opposite signs, so it's not really advantageous. But you kind of get used to that. And then once you have finally killed off a variable, in this case z, you now have a resulting system with one fewer variable. So our system is now 5x plus 3y is equal to 3, and 10x minus y is equal to a negative 1. And essentially you just rinse and repeat. What that means is you just do the same thing you just did, choose a different variable to kill off in this case. So I will choose y to kill off. And I'll go ahead and relabel these. This is row 1, this is row 2. And I will add row 1 to 3 times row 2. And the main reason why is the coefficient of y in row 1 is a positive 3. The coefficient in row 2 of y is a negative 1, so all I need to do is multiply it by 3, and those coefficients will be opposite. Adding that up, let me go ahead and just draw a line here. We have 5 plus 3 times 10, or 30, so 35x. And we'll have 3 plus 3 times a negative 1, so 3 plus negative 3, okay, is 0. And so you get that x is equal to 0. Once you've gotten down to a point where you have a value for one of your variables, you can then back solve. Go back to any of your previous equations with x and y only, so basically in the last step here, and substitute in x equals 0. You can do it into either of those equations, but I will choose the row 2 equation. If you let x equal 0, you'll have negative y is equal to a negative 1, or y is equal to 1. And then, now that we have x and y, we can go back to any of the original equations and substitute in those values for x and y. Again, x was 0, y was 1. So let's go ahead and substitute into maybe the top equation. Why not? So if x were 0, we'd have 0. If y were 1, we'd have 4. And then minus z is equal to 2. And that means negative z is equal to a negative 2, or in other words, z is equal to positive 2, and you are done. Remember to write your answer as an ordered triple here. So it'll be 0, 1, 2. Looks like a system that I probably created during lecture. Finally, normally when you're working on an exam or something like that, you shouldn't be told how to solve a system. They should just say solve. So let's just do one last problem here where we're just told to solve this system. You could do it either via substitution or elimination. Personally, I almost always go for elimination when it comes to systems larger than 2 by 2. So basically all other systems in the universe. So now I'm going to go ahead and choose a column to work with. Specifically, let's go ahead and just work with the x's here. We'll use the x's to kill each other off. So we'll kill off x's there. So I'll take row 1. Let's go ahead and label these really quickly. I'll take the opposite actually of row 1, twice the opposite of row 1. So -2 times row 1, and I'll add that to row 2. That way we'd have a -2x plus 2x. They'd kill each other off. And then I'll also do -3 times row 1 and add that to row 3. So that's my battle plan. And go ahead and do that mathematics. -2 times row 1, add it to row 2. So that'd be a -2x plus 2x. Those cancel each other out. You'd have a -4y plus 3y. That'd be a -y. And then you'd have a -2 times a -z, or a positive 2z, minus 4z, which is -2z. That's -2, sorry. Z is equal to, and again, a -2 times 1 is a -2, plus a -3 is a -5. And then do that again with rows 1 and 3. -3 times x is a -3x, plus 3x is gone. That's beautiful. -3 times 2y is a -6y, plus 6y. That cancels beautifully as well. So we have 0 so far. And then -3 times a -z is a positive 3z, minus 3z is 0. Uh-oh. And we get there, and let's see, -3 times 1 is a -3, plus 4 is 1, and we've got a problem. So when you arrive at a contradiction, and that's literally what this equation is called. A lot of people go through mathematics, they learn definitions, and they forget them very quickly because we don't really use the nomenclature that often. But equations that end up with like 0 is equal to 1, or pi is equal to 5, or -3 is equal to positive 10, or something like that, those are called contradictions. So this is a contradiction here. And if you arrive at a contradiction, that means your system of equations does not have a solution. This is one of those systems that does not have a simultaneous point where they all these planes meet. So that's that system where you had these 3 sheets of paper that kind of met like that, right? So this equation or system of equations has no solution. And we would say, by the way, that it's inconsistent, right? Inconsistent. And I didn't use that language on the other problems, but with the other 2 problems, these are both consistent and independent. So it's consistent because it has a solution, independent because there's only one solution, a finite number of solutions. And the same thing with the previous equation or system of equations. That system is consistent and the equations are independent, again, because there's a finite number of solutions. But the last system we solved, because there's no solution, is called inconsistent. All right, that's it for a review on how to solve large systems or 3x3 systems using substitution and elimination. In the next video, we're going to go ahead and do a parametrization so that if we have an infinite number of solutions, we can actually talk about that.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you listen close. Don't talk too much, that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.